Hey guys, it is time to talk about section 7.5, and we're going to be dealing with some specific properties of logarithms in this section. So up until now we've been solving and evaluating logarithmic equations that have been pretty basic. Today we're going to learn some properties of logarithms that help us to simplify, evaluate, and solve. Those are kind of our main words for this section. Logarithmic expressions or equations that look a little more complicated, but the properties are going to help us to deal with them in an easy way. So the first property that we have, there are three properties today of logarithms. The first one is the product property. So what it says is the logarithm of a product. So here I have one logarithm, and inside my logarithm I have multiplication, is equal to the sum, so adding the logarithms of its factors. So here I'm splitting it up into a bunch of separate logarithms. So if you look at this example, if I have log base 2, here I have 5 times 6. So notice on this side I have one single logarithm, and then inside of my logarithm I have a product. That splits up into the sum addition of two separate logarithms. So when it's a single logarithm, inside it has to be multiplication, and I'm allowed to split it up into log base 2 of 5, so that's the first factor here, plus log base 2 of 6. So let's take a look at how we could apply that. Here it says we're going to use this fact. So this is just something we know. They're saying log base 5 of 2 is approximately equal to this numerical value, and I'm going to use that to approximate the value of log base 5 of 250. So basically when you're doing these kind of problems, you want to figure out a way to split up 250 using 2, because that's the number we're given here, and also if you can get any way to split it up using 5, which is the base of the logarithm. So if I can rewrite 250 in terms of 5s and 2s, I will be able to evaluate it to approximate its value. So for example here, we know that 250 is 5 cubed times 2. How do we know that? Well, 5 cubed is 125, right? So I know, okay, 250 divided by 2 is 125. 125 is 5 cubed. And I can use the product property. So this is the logarithm of a single product. I can split that up into the sum of two separate logarithms. So log base 5 of 5 to the third plus log base 5 of 2. Now I know that log base 5 of 5 cubed is 3. How do I know that? Because if I think about what that means, log base 5 of 5 cubed equals what? If I go back and think about what we did in the first couple sections where we evaluated, I'm saying 5 to the what equals 5 cubed. Well, that what has to equal 3. So basically when the base of my logarithm and the base of my exponent are the same, they undo each other, and I'm just left with this exponent here. So that's equal to 3. And then log base 5 of 2, I can't evaluate that one as easy, but that's why they gave me this value up here. So I replace log base 5 of 2 with 0.4307, and I add those together, and I get 3.4307. So that would be my answer to that one. So using that same idea, I want you guys to try this one. Given log base 2 of 3, how could I approximate this value? So again, you want to see if you can write 96 in terms of 2s and 3s. All right, the answer here is D, 6.5850. And this is what your work should look like. So I know I'm going to try to do something with 3, so I try to figure out, okay, 96, is that divisible by 3? It is. 96 divided by 3 is 32. So I rewrite 96 as 3 times 32. Notice I'm still inside the same logarithm. Then I notice that 32 is 2 to the 5th, so I can rewrite it that way. Then I use the product property. This is a single logarithm of a product. It's going to split up into the sum of two different logarithms, log base 2 of 3 and log base 2 of 2 to the 5th. So I can replace log base 2 of 3 with the value they gave me at the beginning. Log base 2 of 2 to the 5th is 5. And when I add those together, I get 6.5850. All right, second property, the quotient property of logarithms. This is very similar, just has to do with division and subtraction instead of multiplication and addition. So it says the logarithm of a quotient is the difference of the logarithms of the numerator and denominator. So if I have log base x of a over b, so a over b is my quotient, I can rewrite that as log base x of a, that's my numerator, minus log base x of b, denominator. So in this case, log base 2 of 5 6, that's one single logarithm of a quotient. That equals log base 2 of the numerator 5 minus log base 2 of 6. So when it's subtraction, it's separate logarithms. When it's division, it's inside one logarithm. So let's take a look at how we could apply that. Here we have a word problem to do that with. It says the pH of a substance is defined as the concentration of hydrogen ions in moles. Sound like chemistry, right? It is given by the formula the pH is equal to log base 10 of 1 over H plus, the concentration of hydrogen ions. Okay? We're going to learn more later in the chapter about log base 10. Log base 10 shows up in lots and lots of science applications and other applications like that. It's a super common logarithm. So it says, find the amount of hydrogen in a liter of acid rain that has a pH of 5.5. So they give us the formula for finding pH, and we know the pH of rain. So we're going to write the equation and solve for H plus, because that's what we're trying to find. So here's our original equation. They told us that the pH was 5.5, so I replaced the pH with 5.5. And then I need to figure out a way, H plus, my hydrogen ions, that's my variable. So I need to figure out a way to get it out of the logarithm. So what I'm going to do is I'm going to use the quotient property, because this is the logarithm of a quotient. So I can rewrite it as the logarithm base 10 of 1 minus log base 10 of the hydrogen ions. Log base 10 of 1 is 0. Why? Because if I try to evaluate log base 10 of 1 equals what? I'm asking myself, remember if we write it in an exponential form, 10 to the what equals 1. Well, what exponent gives me a result of 1? The exponent of 0. So log base 10 of 1 is equal to 0. And then from there, we end up with this, because 0 minus log base 10 of h is just negative log base 10 of h. I divide both sides or multiply both sides by negative 1. And then I'm going to rewrite this in exponential form using the definition of a logarithm. So 10 to the negative 5.5 is equal to my hydrogen ions. And then I use my calculator to figure that out. It's about 0.000032 moles of hydrogen in a liter of this rain. And then we can check to make sure. So I can plug in what I just got for my hydrogen ions and see if it actually gives me what I think it's going to give me, if it's about equal. And it turns out that it does. If I use the quotient property to write it out, log base 10 of 10 to the negative 5.5, that gives me negative 5.5. 0 minus negative 5.5 is 5.5, so it works. All right, you guys try this one. Okay, you should have gotten C. And there's the work for how we got there. It's almost exactly like the example we just looked at. We're just using a different pH. All right, third and final property for this section is called the power property. This one is interesting. It says the logarithm of power is a product of the logarithm and the exponent. Basically what happens is if I have a logarithm and inside my logarithm I have something to a power, so something with an exponent. That exponent, which in this case is a 5, that exponent of 5 is the same as writing that as the coefficient of the logarithm. So this is 5 times log base 2 of 6. So if we look at this example, we want to approximate the value again of log base 5 of 216. I'm given that log base 5 of 6 is equal approximately to 1.1133. So I'm going to try to write 216 in terms of 6's and or 5's. In this case, I only need 6 because I know that 216 is 6 cubed. So I'm just rewriting 216 as 6 cubed. And then I can bring that power down in front by the power property. It becomes the coefficient. And I know what log base 5 of 6 is. They gave me an approximation, so I plug that approximation in, and I multiply it by 3, and that gives me my final answer of 3.3399. So using that idea of the power property, I want you guys to try this one. Okay, you should have gotten C, 5.1700. And there's the work to go with it. In this case, 1,296 is 6 to the 4th. Then that exponent of 4 that's inside my logarithm can become a coefficient. So I have 4 times log base 4 of 6. Then I can just replace log base 4 of 6 with the value they gave me and simplify. Okay, so we can also use these 3 properties of logarithms to solve equations. Because if you remember back in section 3 or 4, we learned that if I have, let's say, log base 4 of x equals log base 4 of 10, if I have a single logarithm on both sides with the same base, I know that I can drop those off and I say, well, okay, x has to equal 10, right? But that only works if there's a single logarithm on each side. If you look at the example that we're given here, I have 2 logarithms on the left and 1 on the right. So if I want to be able to drop off the logarithms, I need to combine them into a single logarithm on each side. So basically, we're going to use the properties backwards. So here I notice that I have a coefficient. I know that my coefficient can go back and become the exponent of the x, which is what they're showing me here. So 4 times log base 2 of x, that 4 becomes the coefficient of the x. And then we're going to use the quotient property. I know that if 2 logarithms are subtracted, I can rewrite it as a single logarithm of a quotient. So log base 2 of x to the 4th minus log base 2 of 5 is log base 2 of x to the 4th over 5. Notice a single logarithm. There's not a logarithm on the numerator and the denominator. The quotient is inside of a single logarithm. And now I have 1 logarithm on the left, base 2, and 1 logarithm on the right. So that means that x to the 4th divided by 5 has to be equal to 125. And then I'm going to solve. What we did to get from here to here is we multiplied both sides by 5. Remember, multiplying by 5 is like multiplying by 5 over 1. So I get x to the 4th is 625, and when I take the 4th root, so what we did here is we did the 4th root, we get x equals 5. And then, of course, because this is a logarithmic equation, we have to check to make sure that we won't get a negative inside of any logarithm. So we plug in 5 for x. And then we use our properties again. So I bring that 4 to be the coefficient. Log base 2 of 5 to the 4th minus log base 2 of 5. Quotient property, log base 2 of 5 to the 4th over 5. Is that equal? 5 to the 4th divided by 5 is 5 cubed. And it turns out that that does check. Log base 2 of 125 equals log base 2 of 125. So you guys try the same thing, working backwards from the properties, solve this equation. In this case, we get x equals 32. All right, so here's the work. I started by moving this coefficient to be the exponent of what's inside the logarithm, so x minus 2 quantity squared. Then the subtraction of 2 separate logs becomes the quotient inside of a single logarithm, x minus 2 quantity squared over 6. And then now I have a single logarithm on each side, base 3, so I can drop those off. What's inside the logarithms has to be equal. X minus 2 quantity squared over 6 equals 150. To get from this step to the next one, I multiplied both sides by 6. So on this side, the 6 is divided out to 1, and on this side, I got 900. And then since this is x minus 2 quantity squared, I don't need to worry about multiplying it out or anything. I can just take the square root of both sides, just like we used to do in completing the square or anything like that. So I get x minus 2 equals plus or minus 30. So here I end up with 2 answers. X minus 2 could equal positive 30, or x minus 2 could equal negative 30. If x minus 2 equals 30, then x equals 32. And if x minus 2 equals negative 30, then x equals negative 28. I'm not going to show you the whole check process right now. You should have checked. But x equals negative 28 does not work, because if I plug in negative 28 here, I would end up with 2 times log base 3 of negative 30. And I'm not allowed to take a logarithm of a negative number. So negative 28 is not a number that can be part of the domain or the solution set of this equation. So my only answer ends up being x equals 32. All right, that is the end of this section. I will see you in class to practice. I would suggest going back over and reviewing those 3 properties, making sure you have them clear before you come to class.